This is an introduction to numerical modeling. What is a computer simulation? A computer simulation is a mathematical model that is performed by the computer. Maybe a good example of computer simulations is presented in the movie The Matrix.
This is the construct. It's our loading program. We can load anything from clothing to equipment, weapons, training simulations, anything we need.
Right now, we're inside a computer program?
Is it really so hard to believe? Your clothes are different, the plugs in your arms and head are gone. Your hair has changed. Your appearance now is what we call residual self-image. It is the mental projection of your digital self.
This isn't real.
What is real? How do you define real? If you're talking about what you can feel, what you can smell, what you can taste and see, then real is simply electrical signals interpreted by your brain. This is the world that you know. The world as it was at the end of the 20th century. It exists now only as part of a neural interactive simulation that we call the Matrix.
As you can see from the movie The Matrix, a computer simulation looks real, but it is not real. In the Matrix movie, there are 3 layers in these computer simulations. The first layer corresponds to a virtual reality. The second layer corresponds to a code, a computer-generated code that produces this virtual reality. The third layer, the deeper layer of the matrix, corresponds to the source of this computer code. In the matrix, there are a large amount of people that are called the blue pillars. They're happy to live in this computer-generated reality that is called the matrix. A small number of people that they are called the red pillars. They reject the matrix as an interactive simulations, and they wanted to see what is inside of the matrix, and they are able to see the matrix as a pure computer code. And there is a selected person that is called the Neo that carry the source of this code and is able to reload the code and produce a new versions of the matrix. We have also 3 layers in the computer simulations. The first layer corresponds to the visualizations and the modeling and visualization layer that allow us to construct a mathematical model and visualize the results. This is the top layer. In the intermediate layer, we have computer code that are a series of instructions that can be followed and executed by the computer. And this layer, the computer layer of the computer code, is generated by mathematical models that, as in matrix, correspond to the source of this code. In finite element analysis, we have 3 layers too, because finite element is a special example of computer simulations. So the mathematics, the deep layer of the mathematics, correspond to the governing equations of the problem. And these governing equations are presented in a strong form and a weak form. The weak form is used in finite element analysis. The strong form are used in other methods like finite difference analysis. There is an intermediate layer that is the numerical analysis that consists in the conversion of these governing equations into a global matrix equations. These equations can be solved by the computers. Computers are very good solving matrix equations, but they are not good to solve analytical equations like ordinary differential equations or partial differential equations. The third layer corresponds to the modeling and visualization of the results that use computer graphics and rendering techniques. Okay, we are going to go to the modeling and visualization layer in finite element analysis. This is the constructor in matrix where you can load weapons, clothes, training simulations, etc. In finite element analysis, we have a similar constructor where we can load cables, spring dashpot, bars, and beams to make the model. In matrix, you have a visualization layer where you can visualize the computer-generated reality with a certain degree of detail. In finite element analysis, there is also a visualization layer where you can see the results of the simulations. For example, in this case, we are visualizing a model of a stadium, and we can see the displacement of the beam color code. And this is the window that you are going to see in a Strand 7 finite element code. This little window will allow you to control the software, a complete layer of control of the software that includes the modeling of a structure and also the visualizations of the structure. So we are going to learn how to use this tab. As you can see, you can generate files, view results, view the model. You can apply global constraints, create elements, finite element in this case, put attributes to these elements. You can use the tools to change your models. You can include tables with input data. You can select the properties of the elements. You have different solvers where you applied a special kind of finite element analysis in your model, and you can have a visualization of the results. Okay, this is the introductions of the interface, graphical interface of Strand 7 finite element analysis software. We have also more advanced finite element software that is Abacus. Abacus is a very powerful software that allows to model civil engineering problems with high degree of complexity. For example, here we are simulated a drilling procedure. So this is a finite element mesh, and this tool is also a finite element mesh. And here we are looking at the von Mises stress as a special component of the stress. It's visualized by color code, and this kind of model, this is a dynamic model because the model evolves with times. It's also a Lagrangian model. It's a very advanced finite element analysis because in this analysis, the mesh change, evolves in time. Let's play it. So we are drilling this material, and as the material is drilled, there is a change of the stress, high concentration of the stress, and the mesh is going to break apart. So we are going to learn about this advanced software, this Abacus, and we are also we are going to use also the Strand 7 software. That is a very versatile software for structural analysis. It includes a wide range of elements and a wide range of very useful solvers to solve specific problems in Strand 7, both statics and dynamics.